Let's take a look at working with exponential, logarithmic, and hyperbolic functions in integrals. So these integrals are going to lean into some of our basic integration strategies, just our basic integrals, basic antiderivatives, but also going a little bit beyond and definitely working with substitution as we have been doing now for a few weeks. So we're going to jump in here. We're going to try to get through quite a few just for some practice on this video. So this first one, if we're going to get in here and we want to integrate this, first thing we do is we just sort of look at it term by term and see like what rules am I going to use? And so we're going to integrate 3x squared. Well, that's just x to a power, so that's power rule, 1 over x. That's going to be a logarithm. We got a basic exponential function here, x to the pi. Now think about that. Pi is just a number, right? Pi is approximately 3.14, blah, blah, blah. So we can apply our power rule there. We've got another exponential function. It's a base other than e to the x, so we'll have to adjust for that. And then we have a constant. So as I go through this, this is going to be just practice with our basic rules. So we get 3x we take 3x squared, we use the power rule, 3x cubed over 3 minus the natural log of the absolute value of x, using just our basic integration rules here. The integral of e to the x is just e to the x. We're going to use that power rule again. This is going to become pi plus 1 in the exponent divided by pi plus 1. We've got that 7 to the x, so that's going to be 7 to the x divided by the natural log of the base, so divided by natural log of 7, minus, now when we integrate a constant, we get that constant times whatever variable we're integrating with respect to. So it's e squared. Again, that kind of, right, I kind of threw this together with all kinds of different exponent forms, but where we've got the variable in the exponent or the variable as the base, but we also here have just a constant. Both the base and the exponent are a constant. And then, of course, we have our integration constant. Now I'm looking through that to see if there's anything I can simplify, and I can reduce those 3's. So you know what I'm going to do rather than rewrite this? Let's just erase. Yeah, if I can, erase those 3's. There we go. And that is the integral of that first function. All right. So let's keep rolling here. Let's look at number 2. Okay, so on number 2, I'm looking at this and I'm thinking, you know what? I would need to do something here. And there's actually a few different strategies here. We can use U substitution on this, but I want to introduce a couple other little ideas here, kind of lean back into a little bit of algebra here in terms of simplification. When I'm looking at this fraction, this improper fraction in form. And so what do I mean by that? What does it mean to be an improper fraction? Well, an improper fraction is when the numerator is equal or greater than the denominator. And so when we think about rational functions, what we're thinking about is the degrees. And so notice in this case that the degree of both the top and the bottom are the same. So the numerator is equal, or if this had been x squared on top, it would have been greater. And so what we can do, just like with numbers, what we can do with improper fractions is we can reduce the improper fraction to a, we're thinking of this as it's actually a rational function, but we're thinking of, let's just think about the algebra, the arithmetic. We're reducing an improper fraction to a mixed fraction. So here's one thing we can do with long division. So here's one strategy. I'll call this A. Here's one way we could think about this. We could take the x plus 1 and see how many times does it go into 3x plus 1. It's a little review on some long division. This is going to be a quick long division problem. That becomes 3. This is 3x plus 3, and then we subtract. And so the remainder is negative 2. So what we do is we take our improper fraction, 3x plus 1 over x plus 1, and we rewrite it as 3 minus 2 over x plus 1. We take the remainder and put it over the divisor there. So this integral could actually become the integral of 3 minus 2 over x plus 1. dx. So using a little bit of arithmetic, a little bit of algebra with the long division here, arithmetic thinking about improper to mixed fraction form, we can get it into a form that we can actually quickly integrate. Because we can integrate 3, we can integrate 2 over x plus 1. And we're going to come back and we're going to do that one in just a second. But I just want to show you one other way that we could do this. Another way we could do it is we can get creative with the algebra. And I'm going to call this kind of a creative adding. That's what we're going to call this idea, this way to look at it. And so here's what we can do. We can say we've got, so here's just another method, another way to think about this. What's fun about integration problems is there's often multiple ways to do this problem, or multiple ways to do an integration problem. And I want to show you both. They both are, it's kind of nice because we can review in this particular problem, we can review over a couple different strategies. So we take 3x plus 1 over x plus 1, and I'm looking at that and I'm thinking, man, I wish I had, instead of a 1 right here, if there was a 3 right there. So here's my little thought process. If this was a 3, right, if that was 3x plus 3, then I could write that as 3 times x plus 1, and I could factor out that x plus 1 from the bottom. So here's where we're going to get creative. We're going to say, well, what if it was 3x plus 3 on the top? Well, that's not equivalent. Remember, we got to keep equivalency here. So that's not equivalent. That's not equal to 3x plus 1, but it would be if we also subtracted 2. If we just took the 1 and turned it into 3 minus 2. And why would we do that? Well, we would do that because then we can write that as 3 times the quantity x plus 1. We still have that minus 2 kind of hanging out on the outside. And we're dividing by x plus 1, but we can divide each of those terms by x plus 1. And look at what happens. There we get that canceling. We get that 3 minus 2 over x plus 1. And notice right there that we have two different strategies. One kind of a creative adding. We did some adding and subtracting to create that factoring that we were looking for, but we end up with either long division or with our creative adding, we end up with the same result. And that is something that I can integrate. So just two different strategies for integration on that one, but it gives us something we can integrate. We can now integrate 3. I'm going to go term by term here. This becomes 3x. We do still need to integrate the 2 over x plus 1 dx, and that one we do have to use a little bit of beyond the basics, right? We got to do a little u sub on that. So if u is x plus 1, then my du is just 1 times dx. Make those substitutions. This becomes 3x minus the integral of 2 over u du, which is equal to 3x minus 2 times the natural log of the absolute value of u plus our integration constant. So we get 3x minus 2 times the natural log of x plus 1 plus c. And that is my integral. And we were able to integrate that function using just a little bit of creative algebra, or if we wanted to think of it, a little bit of long division. Let's get that all on the screen if I can. It kind of went long on that one. All right, let's take a look at another one. So here we've got a definite integral. We're taking the integral from 1 to e squared of the natural log of x to the 5th power over x. And so this one is definitely a good candidate for a u sub, because if we let u be the natural log of x, we know that the derivative is 1 over x. It's du dx, and then I separate the differential. So there's your dx. But look at that right there. You've got, this is technically, we could write that as 1 over x instead of natural log of x to the 5th over x. And we can make those substitutions. So this becomes u to the 5th, simply du, because the 1 over x dx. I'm thinking of that as natural log of x to the 5th times 1 over x dx to make the substitution. And then this, oh, you know what? We got to do those bounds. So let's let's switch our bounds. This was x equals 1 and x equals e squared. I was about to rewrite those, but let's switch them over to u. So if x is 1, then u is the natural log of 1, which is 0. So this is 0. And if x is e squared, then u is the natural log of e squared, which of course the natural log and the exponential cancel out, and that's just 2. So this becomes u to the second. So this is going to become u to the 6 over 6, evaluated from u equals 0 to u equals 2. And then we can evaluate that. So 2 to the 6 over 6 minus 0. 2 to the 6 is 64 over 6. So this becomes 32 over 3 for that definite integral. And there's our answer. And I do like on that one, that was quick and easy to switch the bounds. So definitely a good strategy on that one. All right, let's see. Let's try to get one more maybe on this video. Let's take a look at this guy. So here we've got 5. We got an exponential function, 5 to the 1 over x. So it's not e to the x, but still an exponential function. And we've got a function in the exponent. So let's let that be our u. U equals 1 over x. Then our du, because that's x to the minus 1, then our du is minus x to the negative second dx. So du is negative 1 over x squared dx, or 1 over x squared dx is equal to negative du. And we have a 1 right here. We've got a 1. This is 1 over x squared dx. And so let's replace that. So we get 5. Let's do the substitutions. We get 5 to the u, and we're going to replace the 1 over x squared dx with a negative du, which of course I put that in parentheses because we're multiplying. So I'm going to put the negative out in front, 5 to the u du. Now let's go ahead and also, same as we did on the previous one, let's switch those bounds as well. So if we have x equals, let's do it in red, switch. If x is equal to 1/3, then u is equal to 1 over 1/3, which is 3. So this is the lower bound is u equals 3. And when x equals 1/2, u is 1 over 1/2. So dividing by a fraction, same as multiplying by the reciprocal. So this upper bound becomes u equals 2. And now we can go ahead and integrate that. The integral of 5 to the u, so we have the minus, the integral of 5 to the u is negative 5 to the u over the natural log of 5. Oh, I should have mentioned, we have this negative here and the bounds are a little bit funky. We could, if we wanted to, if you ever want to flip the bounds, we do have a little rule. Let's write it down here, a little recall. That says if you have the integral from a to b of f of x dx, that is equivalent to negative the opposite of the integral from b to a of f of x dx. And so we could definitely, if we wanted to, I didn't do that. I jumped right into the negative over here. Let's back it up, because why not? Let's use that little rule. It's kind of a nice one. If we see that negative, we see that our bounds are a little, they're a little funky right now because we've got the lower number on top, for lack of a better way to say that. We've got 2 on top and 3 on bottom. So if I wanted to flip my bounds, and I actually already have a negative, so negative of a negative, this is going to become from u equals 2 to u equals 3 of 5 to the u du. And that's just a fact about integrals, an integration fact. So now we can finish it out without that negative. So this becomes 5 to the u, and with the bounds in a nicer order, natural log of 5, and we're evaluating from u equals 2 to u equals 3. And this is going to become 5 to the third over the natural log of 5 minus 5 to the second over the natural log of 5, which we could pull out that 1 over the natural log of 5. And that's 125 minus 25. And this answer becomes 100 over the natural log of 5. And there is our integral, and a little recall on an integration fact. All right, I think we'll stop the video there and we'll do another video with some more integration facts. I do have some more fun examples to look at, and we'll do some with some hyperbolics on the next video.